At this exact moment in our shared timeline, humanity stands on the edge of a situation unlike anything our space agencies have ever genuinely faced. The interstellar object we have been observing so carefully is now rushing toward a crucial transition in its path through our system. This mysterious body, once labeled 3I/Atlas, is moving toward a point that could fundamentally alter how we perceive visitors from beyond the boundaries of our familiar celestial neighborhood. And what makes the situation deeply unsettling is that we are about to lose our ability to see it exactly when something significant may occur. When Atlas first appeared within sensor range earlier this year, researchers around the globe recognized its extraordinary significance. It was only the third confirmed object to arrive from another stellar region, a fragment of some distant cosmic environment delivered into our observational reach. Unlike the frustratingly brief encounter with Oumuamua several years ago, this time we had far more advanced detection tools prepared. From the moment Atlas was identified, it has been tracked with remarkable precision as it speeds inward, now traveling faster than 200,000 kilometers per hour. Throughout this tracking period, its behavior has raised questions that challenge our expectations. Tiny fluctuations in its motion, difficult to explain by standard gravitational models, have been recorded. Its path aligns with the plane where our planets orbit with a degree of precision unlikely to occur by simple celestial chance. An internal composition study suggests an unexpected structural configuration, one not easily explained by natural formation processes known to produce icy debris or rocky fragments. Now, the object is approaching its closest point to the Sun, expected between October 29th and 31st, 2025. This is the moment when solar heat and gravitational forces reach their highest influence. Ordinary comets subjected to such conditions either break apart under internal strain or release dramatic glowing tails as buried materials vaporize into space. This is where scientists hope its true nature will finally reveal itself. However, a critical complication arises. During this same time frame, the object will pass directly behind the Sun relative to Earth. Our telescopes will be unable to observe it due to the overwhelming brightness of the solar disk. For several weeks, we will be completely unable to monitor what happens. It will undergo its most intense phase beyond our sight. When it emerges again, one of three things will be waiting for us to discover. It may persist, change perhaps, but still whole. It may have shattered into drifting fragments consistent with conventional comet behavior. Or there may be nothing visible at all, no trace where we expected to see it continue outward on its escape trajectory. Space-based observatories are scheduled to reacquire at the moment the geometry clears. Radio arrays on Earth will sweep the region. James Webb has dedicated observation time set aside. The world will be watching to see what comes back into view, if anything returns at all. The entire scientific world is waiting, caught between anticipation and dread, to see what appears on the far side of the Sun once the glare subsides. When observational angles open again, agencies such as ESA will direct high-precision tracking arrays toward the region where the object should reappear. That specific zone is not theoretical guesswork. It is the exact corridor through which a mass of roughly 33 billion tons should be traveling if it continued along the gravitational path we calculated. Yet there is a possibility no researcher wants to say aloud. What happens if that space is empty? What if the object does not return at all? Before we leap to speculative explanations, we must examine the established physical possibilities. One scenario is that the object broke apart so completely during its close solar pass that its remnants became too faint and too widely scattered to register. Large icy bodies from the outer reaches of planetary systems can fail in this way. Extreme heating on one surface combined with intense cold on the opposite can induce violent internal stress, enough to tear apart fragile structures. This kind of destructive thermal shock has been seen many times before, but fragmentation leaves signatures that can be detected. Breakups create expanding clouds of fine dust and gas that scatter sunlight, forming luminous streaks across millions of kilometers. These trails remain visible for weeks or longer, and even small surviving pieces follow paths that advanced telescopes can trace. Hubble is capable of identifying fragments only a few hundred meters across at immense distances. So far, none of these expected signs are present. Observatories across different continents, using independent detection methods, have scanned the precise region where recovery should have taken place. They have found no dust plume, no faint reflection, no cluster of diverging fragments. Nothing. Another explanation would involve miscalculations in the predicted path. If our orbital modeling was flawed, if we overlooked an unexpected physical influence, the object may have emerged from behind the sun along a different direction entirely. But months of continuous tracking before solar conjunction provided position and velocity data of exceptional accuracy, relativistic corrections, radiation pressure, gravitational influences. Every significant variable was included. The margin of uncertainty is extremely small. For the object to have strayed so far that we are searching the wrong location would require a directional change vastly larger than any natural process could cause. Not a minor drift, a purposeful redirection. That kind of movement would imply force, deliberate force, the type of maneuvering we do not associate with naturally occurring icy debris or inactive rock. Something that would suggest the object was not a passive traveler, but actively guiding its own path. And that leads us to the third explanation, the one that has remained unspoken through entire conferences and private briefings. A possibility that, if true, would alter not only our understanding of this visitor, but our understanding of where we stand in the larger cosmic story. Harvard researcher Avi Loeb has been issuing increasingly direct cautions ever since his team examined the unusual slowdown characteristics recorded months ago. He has asked a question that is now growing harder to avoid. What if the object's disappearance behind the sun is not an accident of timing? What if the interval around October 29th is a perfect, prearranged moment for a controlled change in course, completely shielded from all observation by the sun's overwhelming radiation? To understand why this moment matters, we need to look at an idea in orbital physics known as the Loeb effect. It describes how applying thrust at the point where an object is moving fastest, deep inside a massive gravity well, dramatically increases the efficiency of that thrust. In other words, a small push when moving extremely fast near a powerful gravitational source can alter a spacecraft's path far more than the same push applied elsewhere. Perihelion, the object's closest approach to the sun, is exactly that point, the deepest part of the sun's gravitational descent. If this visitor has any form of propulsion tucked within its unusual, possibly hollow structure, then this is the most advantageous moment in its entire journey to use it. Even a minor change in speed, just a few hundred meters per second, would be enough to completely transform its route. A trajectory that once looked like a one-time pass through our system could become a closed orbit, keeping it here permanently. Or, with precise timing, it could re-aim itself toward a new destination, perhaps the asteroid belt, or a stable position in the outer system far from Earth's direct surveillance. The fact that our ability to observe it drops to zero during this exact interval makes the timing deeply unsettling. For several weeks, the object is hidden behind a screen of solar plasma more than 1 million kilometers across. No telescope, no radar, no orbital platform can see through that glare. If a maneuver is carried out, we will only learn about it after the maneuver is finished. When observational access returns in December, we may find that it has shifted onto a new trajectory, or that it has slipped entirely beyond our search limits. A clean escape, or a deliberate repositioning. Now consider its behavior before entering this blind interval. Its entry angle into our system nearly matched the plane of our planetary orbits, a statistically rare alignment for something wandering in from interstellar space. It was recorded gradually slowing in a way that does not match known cometary outgassing or pressure effects. Its density reading suggests internal cavities rather than solid mass, a configuration that makes little sense for a naturally formed object, but all the sense in the world for something manufactured to minimize weight while protecting interior components. And months ago, it endured a blast from a solar plasma eruption, a surge of charged particles powerful enough to tear apart any fragile, loosely assembled icy body. Yet it remained structurally unchanged. Taken individually, each of these anomalies could perhaps be argued away, but together, they outline a pattern that no longer resembles simple chance. The timing, the movement, the structure, the resilience. It behaves less like a drifting relic and more like something following a plan. It has maintained an unusually steady rotation over months of tracking, so steady that it stands in complete contrast to the irregular, chaotic spin expected from objects formed through natural clumping and collision. Randomly assembled celestial bodies simply do not exhibit this kind of rotational precision. But perhaps the most statistically revealing detail came on October 3rd. On that date, it passed Mars at just 29 million kilometers, an alignment so exact that the probability of it happening by pure chance, when calculated across its entire interstellar entry trajectory, is estimated at less than 1 in 50,000. In simpler terms, the timing was too perfect. Now, of course, each anomaly on its own could be rationalized. One could argue that its resilience is due to an exotic internal composition, that the Mars flyby was an extraordinary but ultimately random coincidence, that its deceleration is caused by some unfamiliar sublimation process we have yet to observe in our small sample of interstellar travelers. But when all of these traits are examined together, not one by one, they form a pattern, and in nature, persistent patterns are rarely accidental. They usually point to some underlying organizational principle, whether that principle arises from physical laws we don't yet understand or from deliberate engineering. What makes the situation especially unsettling is how it differs from our first known interstellar visitor in 2017. Oumuamua behaved strangely, yes. It accelerated without any detectable gas emissions, and its elongated form left room for speculation. But at the end of the day, Oumuamua followed a predictable escape trajectory. It arrived, it acted oddly, and then it exited the solar system along a track we could measure and model. 3i/Atlas is not following that script, if its earlier behavior is any indication, and if it does, in fact, use the Loeb effect during its hidden close pass behind the sun, then it may not simply drift away. It may rear out entirely. It may shift its orbit without warning. Or it may disappear from every predicted position at once. That possibility alone forces us to reconsider what we think we know, and notice the global response. NASA's public statements remain cautious and noncommittal. ESA acknowledges a sudden observation blackout, but has leaned toward fragmentation as the current working explanation. Meanwhile, China has issued no public comment since the Mars alignment. This kind of synchronized restraint has precedent. It does not point to conspiracy, rather to institutional caution. When data has the potential to redefine our assumptions, agencies try to avoid premature conclusions. Announcements, if they come, must be carefully timed, carefully worded, and agreed upon internationally. The next few weeks will determine everything. Telescopes across the world are conducting systematic scans. The James Webb Space Telescope has scheduled observation windows. Ground-based radar networks are sweeping every coordinate where it should reappear. And if it does not reappear, if it is simply gone, if no predictable natural mechanism accounts for its absence, then we will find ourselves facing possibilities we have never seriously had to consider before. Concealment, active maneuvering, intentional departure, timed precisely during our moment of blindness. No matter how this ends, natural or artificial, intact or fragmented, its impact is already profound. It has forced our scientific worldview to expand. It has reminded us that the universe does not exist to fit our comfort, and it has made one truth unmistakable. Sometimes, the greatest discoveries begin with something that refuses to behave the way it should.